Welcome back to Neural Intel, everyone. For this deep dive, imagine an AI agent, maybe a robot, that could explore your house, map it out in its head.
And actually remember where everything is.
Exactly. Even if you move the furniture around, it remembers the changes. And then hours later, it uses that memory to do something complex, like finding something specific across multiple rooms.
That's pretty much the frontier we're exploring today. How these embodied AI agents are getting much, much better at remembering their environment. We're talking long periods, different places.
And our source is a fascinating research paper that introduces a new model and a new benchmark to test exactly these kinds of long-term memory skills in 3D.
Yeah, the model's called 3DMEM-BENCH.
Right. So our mission, as always, is to dig into the technical side. We want to unpack how 3D-LLM-MEM works, how it tackles this, frankly, huge challenge of giving AI a solid, spatially aware memory.
And how that unlocks these quite surprising new skills, like navigating based on things it saw way, way earlier. We'll stick to the tech details, avoiding the ethical angles as usual. For updates on papers like this, check out our webpage linked in the bio.
Okay, let's dive in. First off, why is memory so hard for these AI agents? Especially in, realistic 3D worlds, like the ones shown in the paper's diagrams.
Well, think about it. Navigating a complex space, like a multi-room house, isn't trivial even for us sometimes, for an AI.
It's not just one static room it has to deal with.
Precisely. The big problem is that many current AI agents have a very limited memory, often called a context window. They basically only remember what they're seeing right now and maybe the last couple of actions they took.
Okay, so that works if you tell it, pick up the cup right in front of you.
Sure, simple stuff. But what if the task is more like, remember that blue cushion you saw in the bedroom half an hour ago? And now I could put it on the sofa in the living room.
The short context window is totally useless then. It's forgotten the cushion long ago.
Completely useless. It just breaks down. You need what the paper calls long-term spatial-temporal memory. Remembering what object was where, and crucially, how things might have changed over time as the agent moved around. Did someone move that cushion?
Right, tracking changes.
Yeah, and this paper really tackles a gap. How do you use these powerful large language models in embodied agents, but give them a persistent memory using rich, dense 3D data, not just text or recent images?
Okay, so that's the challenge. How does 3D-LLM actually solve it? It sounds like they took some inspiration from us.
They definitely did. The core idea in 3D-LLM-MEM is this specialized memory system built into a 3D embodied LLM. And yes, it's a dual memory system, kind of like how human memory is often described.
Dual memory. Okay, break that down for us. What are the two parts?
So first, there's the working memory. Think of it as short-term limited capacity. It holds what the agent is experiencing right now, current sites, recent actions. This bit stays right there in the model's immediate focus, its context window.
The here and now buffer. Got it. And the other part?
That's the episodic memory. This is the big one, the expandable long-term store. It archives past spatial-temporal information, memories of places visited, objects it saw, the history of its exploration.
And this isn't just storing snapshots, right? You mentioned dense 3D representation.
Exactly. That's key. It's not just saving flat pictures, it's capturing a richer, three-dimensional understanding of the environment. How objects are arranged in space, their relationships. It's a much more powerful way to remember a scene.
Okay, so you've got the current moment buzzing in working memory and this huge library of past 3D experiences in episodic memory. How does the agent connect the two? How does it know which old memory is useful now? That seems like the real magic trick.
It is, and that's where their memory fusion module comes in. This is the clever part.
Huh?
Its job is to actively pull the most relevant information from that vast episodic memory and combine it, or fuse it, with what's happening in the working memory right now.
So it's not just passively storing, it's actively querying its own past.
Yes. Based on the current situation, technically it works like this. It takes features, basically numerical descriptions, from the working memory, what it's seeing and doing now. Let's call that the query, FQ2.
Okay, the query is the now.
Right. And it uses this query to search through the episodic memory bank. The episodic memory stores its past observations using key features, which are like tags or addresses for memories.
Like index entries?
Kind of, yeah. And value features, which hold the actual rich 3D content of that memory.
So the agent's current perception becomes a smart search term for its own history.
You got it. It uses an attention mechanism, specifically a memory query attention process, to find the keys that best match the current query FQ22, and then retrieves the corresponding rich values.
And the result of this search?
The result is a fused memory feature. This is an enhanced representation that blends the immediate situation with the most relevant bits of the past pulled from episodic memory. That fused representation is then fed to the LLM part of the agent to make better decisions, plan better actions. It's like getting the perfect flashback just when you need it to solve the current problem.
Okay, that makes sense. How does the episodic memory itself get built and updated? Does it just grow indefinitely?
Well, as the agent moves around, the recent experiences from its working memory, the stuff it just saw or did, get transferred into this episodic memory bank for long-term storage.
So working memory contents graduate to episodic memory.
Essentially, yes. And importantly, if the agent revisits a place and observes a change, maybe an object was moved or a door opened, the corresponding memory trace in the episodic bank gets updated, so it stays current. The paper notes they use some pre-collected data in the simulator to handle this efficiently during training.
Okay, this memory system sounds powerful, but you need a way to measure if it actually works better, right? Especially for those tasks that really lean on long-term recall. You mentioned they built a new benchmark.
Absolutely necessary. The existing benchmarks, well, they just weren't set up to really stress test this kind of long-term multi-room spatial temporal memory. So the researchers created 3DMEM-BENCH.
Tell us about 3D-MEM-BENCH. What makes it so tough?
For starters, it's big. Over 26,000 trajectories, nearly 1,900 specific tasks, and its entire design philosophy is about pushing the boundaries of long-term memory in these complex 3D scenes.
What kinds of tasks are we talking about?
Several flavors. First, embodied tasks. These are action sequences where the agent has to remember earlier steps or observations. Think about that example. Prepare a suitable present box for the teddy bear.
Right, the multi-room scavenger hunt.
Exactly. Find the bear in room A. Find boxes in room B. Maybe test fit. Find wrapping paper in room C. Then remember which box in room B was the right size and go back to it. Impossible without good memory. Or the simple breakfast task shown in the paper, finding milk, cereal, bowl, spoon, all potentially in different locations, remembering what you've got and what you still need.
Yeah, looking at those diagrams, you can see how an agent with only short-term memory would just wander aimlessly or get stuck repeating steps.
Totally. Then there's EQA embodied question answering. Here, the agent doesn't just act, it has to answer questions about its journey and the environment based on its memory.
Like what kind of questions?
Things like which carpet, the one in the hall or the one in the study, has a larger area now, maybe after it potentially interacted with one. Or captioning tasks, like summarize the key differences between the kitchen and the bedroom you explored. This really tests if it built a coherent memory.
So reasoning about space and changes over time.
Yes, and they categorize these EQA tasks further. Spatial reasoning, long-term object navigation, like go back to the apple you saw earlier, comparing things, understanding multi-room layouts, even counting objects scattered across the whole explored area.
Does it vary the difficulty? New environments.
Oh, yeah. Tasks are rated simple, medium, hard, often based on how many rooms or steps are involved. And crucially, they test in two settings, in domain, where objects and layouts are similar to the training data.
Familiar stuff.
Right. And in the wild, using objects or arrangements the agent has never specifically seen before. That really tests generalization. Does the memory system cope with novelty?
Okay, the setup sounds rigorous. So the million-dollar question. How did 3D-LLM actually do on 3D-MEM-BENCH? Did the fancy memory system pay off?
It really did. The results showed 3D-LLM significantly outperforming the existing methods they compared it against. And the difference was most dramatic in the really challenging scenarios.
You mean the harder the task got, or the more unfamiliar the environment, the bigger the lead for 3D-LLM?
That's exactly it. Methods that rely more on limited context, their success rates just tanked, especially in those in-the-wild settings and on the hard difficulty tasks. 3D-LLM proved much more resilient.
Can you give us a sense of the numbers?
Sure. For instance, if you look at the average success rate for all embodied tasks combined, but specifically in the challenging in the wild setting, 3D-LLM hit about 32.1%. The baseline methods were significantly lower.
Okay, that's a noticeable improvement in unfamiliar territory.
And it gets even clearer if you zoom in on the hard tasks within that in the wild setting. The really tough stuff. Baseline success rates could drop way down, maybe around 5% or so in some cases, but 3D-LLM was still managing nearly 28% success. That really highlights how crucial that robust long-term memory is when things get complex and unpredictable.
Wow. Okay, so it holds up much better under pressure. What about the question answering, the EQA and captioning?
Same story there. Superior performance from 3D LLM-MEM, as you'd expect, since those tasks directly target reasoning over remembered information across time and space. The paper's tables show this clearly. Baselines, even language models fine-tuned for 3D environments, but lacking this specific memory architecture, really struggled with EQA questions that required recalling details from much earlier in the trajectory. It confirms that just having a big LLM isn't enough. You need the right memory structure.
So they showed it works well. Did they dig into why their specific design, particularly that memory fusion part, is the key? I think you mentioned an ablation study.
They did, yes. Ablation studies are great for this. You basically take your system and systematically remove or change specific components to see what breaks or gets worse. It helps pinpoint what really matters.
And what do they tinker with here?
They focused on that memory fusion module, specifically the query part, the signal that searches the episodic memory. Remember he said 3D LLM uses the current working memory features as the query?
Right, and now searches the past.
Exactly. So they tried other ways to generate that query. What if you just use the most recent memory added to the episodic bank as the query? Or what if you just use some generic, learnable parameters not directly tied to the current context?
Simpler approaches, basically.
Simpler, perhaps less context-aware approaches. And the result was pretty clear.
Let me guess.
Yeah.
Using the working memory, the current context, worked best.
By a noticeable margin, performance dropped when they used those alternative query methods. It really validates their design choice. Grounding the memory retrieval process in the agent's current perception and task context seems critical for pulling out the relevant past information. The here and now really is the best guide to finding the most useful bits of then and there.
Okay, so pulling it all together, what's the big picture here? What do these technical steps forward with 3D LLM mean for embodied AI?
Well, stepping back, it means we're getting closer to AI agents that can operate in the world with a memory that feels maybe a little more human-like. They can build up experience over time across different places and actually use that experience effectively.
It feels like a fundamental capability they've been missing for truly complex tasks.
It really is. This dual memory idea, combined with the smart fusion mechanism and using those rich 3D representations for memory, looks like a very promising path forward technically. It lets agents tackle tasks that inherently require remembering and reasoning over extended periods and distances. Things like, complex assembly, using parts found in different locations, or adapting behavior based on changes observed over time.
Are there limitations they acknowledge?
Oh, sure. They're quite upfront that their current implementation relies on fairly high-level actions provided by the simulator, things like go to the kitchen, pick up the apple. It doesn't handle the really low-level motor control and navigation planning from scratch.
So it knows what to do based on memory, but the simulator handles the fiddly bits of how to walk there or grab something.
Kind of, yeah. But they position that as a separate challenge, something that could potentially be integrated with their memory system in future work. It's about combining this powerful memory with sophisticated physical control.
Okay, so summing up this deep dive. The big leak with 3D LLM is giving these embodied AIs a much more robust, almost human-inspired long-term memory that's specifically designed for navigating and remembering complex 3D spaces and the events within them over time.
Yeah, it fundamentally expands their ability to understand and act based on more than just what's immediately in front of them or what they just did. It's about context, history, and change.
Which leads to a fascinating thought to leave you all with.
Yeah.
Consider this. Once robots and embodied AI truly master this kind of long-term spatial-temporal memory and reasoning, what kinds of incredibly complex multi-step tasks could become commonplace? Think about dynamic, messy, real-world environments, warehouses managing inventory, assistants in hospitals, maybe even complex search and rescue operations. What becomes possible when they can remember everything they've seen and done over hours or days in constantly changing 3D spaces?